Hi everyone, I'm Melinda Malley. I'm going to talk to you today about ICRA2020, Design and Algorithms for an Adaptive Self-Assembling Soft Robot Collective. So why would we want to have adaptive self-assembly in robots? Using self-assembly, robots can form structures that adapt to unknown environments, for example, going from one cliff to another. And structures can adapt over time. So they can even dissolve when no longer necessary. So social insects do this really well. Everything from honeybees, which form ovens to cook hornets to death, to fire ant rafts and weaver ant chains. So what we'll focus on for the most part today are army ants, which form bridges and even their nests from their own bodies. So this is a bridge formed by Eceton hamatum. As we can see, the bridges are really incredibly resilient. Even when we destroy them, the ants can reform them in under a minute. So they do this by simply following local rules with no apparent leader or centralized control. Bridges can conform and adapt to their environment and form in response to high traffic, as shown here. So here the bridge is pretty much completely reformed, but if traffic stopped, it would dissolve. So this really allows ants to readily adapt to new situations. So this is Eceton Robotica, which is a robotic platform for adaptive self-assembly. The robot agents are soft, flexible bipeds, and to move, the robot simply flips until it senses a surface, and then it can attach one gripper, and then detach the other gripper to continue to move. This is the Eceton Robotica robot module. The body is composed of alternating rigid and soft flexible segments, and the robot is covered in stretchy Velcro. DC motors attached to cable spools wind the cable on one side while unwinding on the other side to allow the robot to flip. The gripper is on either end of the robot, and it's composed of 4 corkscrews, which are controlled by a DC motor, as well as 2 IR reflectance sensors, which let the robot sense a surface to attach to. The corkscrews wind to connect to the Velcro covering of other robots. As shown here, robots can use the corkscrew grippers to climb over other robots. As shown in the following clip, robots can also sense if another robot is attached to them. The top robot sends a vibration pulse before and after attaching to any surface, and this is indicated by the pink LEDs. The bottom robot lights up when it senses it has been stepped on by another robot, so that's also indicated by the pink LEDs. So how do we communicate through vibration? A vibration motor is placed on the inside of the gripper, and the motor pulse is sent from the gripper through the robot body, and then detected by the IMUs. So the robot can sense a vibration pulse at any location along its body, as shown here. Raw data from a vibration pulse is shown on the bottom left. So about 3 samples are taken per cycle of the vibration motor. The derivative delta of the raw data is shown on the bottom right, calculated as the difference between each consecutive sample. So by thresholding this value, the robot can detect vibration pulses. And the robot collects about 15 samples of the acceleration values, then computes this delta value and compares it to the threshold. So if at least 3 delta are above the threshold, a robot is detected. To see if robots following a simple rule could form and dissolve structures, we created a simplified model of the robot in simulation. So the model flips and grips to climb in the same manner as the real robot. Robots follow a simple state machine inspired by army ants. When a robot senses it has been stepped on, it stops moving and goes into a bridge state, joining the structure. If a robot in the structure has not been stepped on in some time, it can try to move and return to walking. Robots in simulation move across a V-shaped terrain inspired by army ant bridge experiments. So these are our experimental parameters. Using the delay between robots shown on the left, we can control the traffic rate, and we also varied the geometry of the terrain. So here's what a simulation looks like at very low traffic levels. A very small bridge might form, and then traffic will stabilize. So at higher traffic levels, robots are closer together, and therefore they're more likely to collide. So this leads to more robots in the bridge structure, and bridges forming higher up along the V angle. So we also tested bridge dissolution. Here traffic is stopped, and when robots no longer feel other robots gripping them, they are allowed to leave, and the bridge dissolves. So this is a picture of the simulation results for bridge formation. At low traffic levels, bridges may not form at all, and then as traffic increases, as we saw, more bridges form. If traffic is very high, then we may end up with a stacking situation where robots stack on top of each other. So we ran a parameter sweep with 10 experiments per V angle and traffic level. Here the x-axis shows the V angle from narrow to wide. The y-axis shows traffic level as the mean distance between robots in body lengths, and the numbers are the average number of robots in the structure over the 10 experiments. Bridges are more likely to form in tighter angles and at high traffic levels where there's a smaller distance between robots. When traffic is too tight, again, robots start to stack on top of each other, shown in the red. This actually occurs with real ants as well, but since they're not restricted to 2D, unlike our experiments, they can go around and reduce the pileup. So this is the results for bridge dissolution when traffic was stopped. So most bridges could actually completely dissolve. Here the grayscale shows the average percent of dissolution, and the numbers represent the average number of robots left in the bridge. Only about 11% of bridges did not completely dissolve, and of those cases that did not dissolve, what we call up grabs, double grabs, and repetition prevent dissolution because one robot is attempting to move, but it's beneath another bridge robot. This could be remedied by adding stochasticity to the design, which may allow that top robot to move. Finally, geometric errors occurred because robots became stuck in the terrain. Robots are allowed to move, but cannot, and that's because unlike the hardware system, it lacks the compliance to move through the tight space. Finally, we focused on V-shaped terrains. However, the local control rules in simulation can also be expanded for more complex terrains like the one shown here, where robots are able to form and dissolve structures. So in this paper, we demonstrate a robot hardware system for Army-inspired adaptive self-assembly where robots can climb and attach to each other on any point along their body, sense if another robot is attached to them. Finally, we demonstrate that using local control rules, simulated robots can form and dissolve structures.